Hey, what's up, guys? This is Jun here. So today, let's take a look at this 1074 number of submatrices that sum to target. So it's a hard problem. Okay, let's take a look at the description here. So you're given like a 2D matrix and a target. So, and it just asks you to return the number of non-empty submatrices whose sum is equal to the target. Okay, so here it's just telling you that what is defined as a matrix, and how you define the two matrices are different. Those are kind of like a subtle. And here are some examples here. So the first one, let's say we have this like 3 by 3 matrix, and then the target is 0, right? So, and the answer is 4, right? So 1, 2, 1, 2, 3, and 4. So that's the 4 sub matrices. And here it's 5. So why is 5? Because we have 1, minus 1, minus 1, and 1. So how do we get this 5 here, right? So we have one submatrix, right? That's 1, that's 2, right? And this is 4. So this is 3, this is 4, and the entire thing is 5. That's how we get 5. Okay. So first thing first, right? The brute force way. We can always do what? We can always do try to find all the submatrices, and then we do a 2D pre-sum, and then we just get each submatrices sum, and then we compare with target. So if we do that, right, that's going to be m square times n square time complexity. And with that, I think most likely it's going to be TLE here, because we have a length of 100, right? So to improve that, we have to find a better way, right? I think a common strategy, whenever we see like a 2D problem and ask us to find the sum, right, of a matrices, so we can always like fix either a column or a row, two column or two rows, and then we compress the row or column in between, and then we convert this 2D problem into 1D problem. Let's assume we fix two rows here, sorry, two columns here, and we compress that all the values in between. Now we have a 1D array here. Okay, so now the problem comes down to the what? With a 1D array here, with the different numbers here, right? The different numbers here, and with a given target, uh, given target k here. What are the numbers of subarray whose sum equals to the target k? That's gonna be a different like a 1D problem, right? So to solve that, so now how can we solve this problem, right? So the best way of solving this problem is to what? Is to use like a hash table. Basically, the way we are solving this like a number of subarray whose sum is equal to k is we use the hash table. It's gonna be actually it's more like a DP, right? So I'm going to like have like hash table, right? Here. So the key and the value, right? So the key is the sum, and the value is the frequency. Is the frequency for this sum. And every time when we have like a running sum, basically we're keeping like a running sum here, right? Running sum. And every time we get a running sum, right, we'll do a running sum minus k, and then we have a target sum, right? And if the target sum exists in the hash tables, we just add that frequency to our final answer. And of course, and in the end, we'll be updating the frequency for the current running sum. And so how will this thing work, right? Why this thing works? So let's say we have I'll give an example here. So the example is like this. We have like, let's say 1, 3, minus 2, 2, and 2. Okay. And let's say the k is equal to 2. So what is the running sum? So we have so the running sum, right? The running sum is 1, 4, 1, 4, 2, 4, and 6, right? So let's assuming we are at 6 here. Okay. We're at 6 here, and 6 minus 2, so 6 minus 2 equal to 4. Basically, our target sum will be 4. And we'll be looking for like this 4 in the hash table. As you guys can see, we have like 2 4s uh, uh, be, before 6. So that's why we will have like the frequency of 4 will equals to 2. So it means that, when we're at 6 here, we're looking for 4 here, and we find 2 4s, right? Which means that there are like two, basically there are two subarray whose sum is 2 up until this up to this position. So why is that? And as you guys can see, so what are those two subarrays, right? So the first one is this 1 3 1 3 minus 2, right? So that's the first subarray that will get us to the 2. Sorry, my mistake. What am I looking at here? So the first one is this one. That's the subarray 2. Basically from this 4 to 6, we have a 2 here, right? That's the first one. That's the first subarray ending at this position, right? Ending at this position. And second one is what? Second one is like it's this. It's 2 minus 2 to 2 minus 2 2 and this one. This is the second one. And that's how we get the second 4 here, right? As you guys can see, we have 2 4. So the first one is as if we from the 6, between the 6 to this 4, we have the first subarray, and the second one is between the 6 and the other 4. We have another subarray, right? That's how we use this frequency to help us track how many subarrays we have seen so far. Okay. All right. So with those two things in mind, we can start our coding. So the first thing is I'm going to use a pre-sum, right, to help us to squeeze, to compress the 2D problem into 1D problem. So this is like a common techniques you guys should know. So now we have 0, right? So that's that. And now I will populate. I'll populate those the 2D pre-sum. Okay, now I have the current sum equals to this for j in range n if j equal to 0. Okay, current. So because we have the first element, right? That's why I'm going to do this. Actually, another way of doing this is we just pad this pre-sum with a 0. Okay, that's one way. But for that, later on when we do the loop here, we instead of from 0 to m minus 1, we have to loop through 1 to m plus 1. That's gonna uh, I I I'm not a big fan for that. So that's why I'm going to stick with the original size here. You know, ij. That's why I need to handle this uh, j, the first column separately, so that the array, the index will not be out of the boundaries. You know, so here we have a matrix. You know, I, j plus, right, current sum minus 1. Okay, so that's that. And then in the end, we do a pre-sum dot append current sum, right? So that's that. And now later on, so here we have answer equals to 0. So fix two columns, right? So the first one is C2 in range n, and sorry, that second one is C2. So the first one is C1 in range C2 plus 1. So we do a plus 1 because even we want to include a single column case, you know. So that's why we have a current array here equals to 0, equals to not 0, the empty list. Sorry, it's my Chinese input here. So for I in range m, right? So because for each row, I want to compress the values in between those two columns. So the row sum equals to the pre-sum I C2, right, minus pre-sum I C1 minus 1. Okay, so that's another thing we need to be careful, since you know the C could start from 0. If when C1 equals to 0, this will be out of the boundaries. So that's why I'll do a check here, C1 greater than 0, right? Else 0. Yeah, I mean that's the a small catch if we're using the original size. You know, if we do a paddings, we initialize everything with 0, with a size m plus 1 and n plus 1, right? So here, I mean, we start from 1 plus n, right? And then here we also from 1 to C2 plus 1, and then here we don't have to worry about these things here. I mean, just a small trade-offs. You guys can choose whatever you want. At least for me, I'm sticking with the original size here. Okay, so the current array, right, dot append the row sum. So in the end, I have like a compressed 1D array here. So all I need to do is I just need to create like helper functions to help me get what get sub array count, right, with target, right? So here I'm going to pass in this array here, and then in the end I simply return the answer. So now this is what I mean convert 2D problem into 1D problem. Now all is left is just to implement this helper function, right? So define that we have an array here. So like I said, you know, we're gonna use a hash table to store the frequencies of sums. Okay, I'll just use a sum dictionary, and then as default we have a dictionary, right? With int, and then we have answer equals to 0. So you know, and then the running sum, right? The running sum starting with 0. Now we have a I for num in this array here. First we do a running sum, right? And then plus numbers, and then we have a target sum. The target sum equals to running sum minus target. and then we check if the target sum in the sum dictionary. Okay, and then we just do an answer plus the sum dictionary, the frequency of that, basically with the target sum, right? And then later on here, we just we update the sum dictionary, the frequency of the with the current running sum here plus one, right? And then in the end, we simply return the answer. Okay, but there's like a small things we need to be careful here. The thing is like this. Let's say we have this array. It's like 1, 2, as simple as this, and the target. Sorry, and the target is 3 here. So we should return 1, right? Because 1 and 2 has the sum equals to 3. But if we follow our logic here, let's say we have 1 here, right? So at the beginning, the running sum equals to 1, right? And the target is it's equal to 1 minus 3, which is going to be a minus 2. And the minus 2 is not in the dictionary, so we'll skip. Okay, so now we have a dictionary. We have a dictionary like this, right? So 1 and 1. And when it comes to 2 here, so the running sum is what? Is 3, right? The running sum is 3, and 3 minus 3 is 0, but still 0 is still not in the dictionary. But as you guys can see here, 0 is a special case. It means that if the subarray, if the one of the subarray starts with the first element, okay, then we need to have like a base case with a sum equals to 0, so that we can count this array. We can handle this case, right? So that's why after we create the sum dictionary here, we're gonna start with 0 with 1, so that here we can accumulate that 1 into our final answer here. All right, yep, that's how we calculate the this count of the subarray, yeah, with the target here. And this is a very useful uh, sub problems. I think you guys should try to remember it. Should at least remember the concept and the logic. As you guys can see, this one can be combined with some other techniques and then form a hard problem. So it's better to master this the sub problems first. Okay, so let's try to run the code. Oh, dumb. Sum. Okay, right. Answer, run the code. All right, cool, accept it. Submit. All right, cool. So accept it. All right. So how about the time and space complexity, right? So I think it's pretty straightforward, right? So here, I think this is the most expensive part. So we have m times n. No, this is like the n square, right? So this is the n square, and we have like O of m here, right? And here the sub problems here. So this is like a O of m as well, right? So it's only a single for loop here. So in total, this problem is gonna be a n squared times m, right? So that's that. And the space complexity is the m times n, because we have that presum stores here. That's gonna be a 2D array here. And this is the time complexity. When we fix two rows here, two columns here, you know, we can also fix two rows here. So in that case, the time complexity will becomes m squared times n, Cool. I think that's it for this problem. Thank you so much for watching this video, guys. Stay tuned. See you guys soon. Bye bye.